Hi, I'm Divya and Persaud. I am a PhD student at UCL's Mullard Space Science Laboratory with the Imaging Group, and I will be talking about 3D imaging and visualization of the surface of Mars to study geology. So why do we care about 3D? Geology on Earth is studied in 3D, so geologists go out in a field, they look around themselves, they understand the geometry of the rocks around them in 3 dimensions. But unfortunately, in planetary science, we don't have a lot of information taken from the ground, with the exception of astronauts on the moon and Mars rovers and other landers on other bodies. But all of that data is also really limited. So if we want to study geology over a wide region on a planet, we have to use orbital data. So that these are images that are taken from space by orbiters, probes, and spacecraft performing flybys. So these are spacecraft that are either dedicated to looking at the surface of a planet or a moon, or just flying by, capturing what they can on their way to their destinations. So this orbital data is in map view. You're looking down at the surface rather than being on the surface and looking out to the horizon. So this changes how we intuitively look at the geology. So I, as a geologist, when I look at a 2D map, I have to think very differently about what I have to understand about the processes that formed a landscape compared to when I'm actually out in the fields looking at rocks up right in front of me. And this changes how anyone understands the surface. We all, or most of us, use our eyes to understand the world in 3 dimensions, or else use our sense of hearing to understand the world in 3 dimensions. And so this is an issue not just for scientists, but also anyone who wants to learn about a planet. So the human brain is able to understand 3D using 2 different tools. So our eyes, as shown in this little diagram, are spaced out on our face. And that means that each eye sees anything we look at from a slightly different angle than the other eye. So we're getting different information from the eyes, and then our brains are able to process that information and actually understand depth and shape. And there's some other things that our brains can do to help process the information that we get from the world around us into 3D images. So computers can do something pretty similar. So if we give a computer 2 images of the same area, so these are orbital images looking down at a surface of a planet, and say this computer has the processing capability that mimics the human brain, it can extract 3D information. So this little animation on the right is showing my study area from 2 different angles. So you're seeing the left and the right images. And each image is showing a slightly different view of this area, and you're getting different information, right? So the computer or a computer program can take those different bits of information if they know where the camera was when it took these images and resolve that into 3D data. So I've applied 3D imaging in particular to an area on Mars called Gale Crater. So this is the Curiosity Rover landing site. And in the little map in the corner, you can see a little star that says MSL, so that's Curiosity Rover's current location approximately. And Gale Crater is really interesting because there's evidence of aqueous activity, which means water. So we see channels, we see deltas. The geochemistry that the rover has studied suggests a lake environment. So there's a lot of evidence of water that has been active over a certain period of time. Gale Crater is also really interesting because there's the central mound right in the middle. So if you see this little mountain in the middle of the map, and also in a 3D perspective view at the bottom of the screen, this is Aeolis Mons, or Mount Sharp. So this is a pretty tall mountain. We don't really know how it formed, whether it was deposited by water or by wind or even volcanism or by the impact that forms the crater itself. And this has been a mystery for a long time. And so Curiosity Rover is slowly climbing up Mount Sharp to figure out how it formed. So with regards to 3D processing, I've done 3 stages of 3D processing from 3 different cameras. So from a bit of a lower resolution, 12.5 meters per pixel, up to 25 centimeters per pixel. So the smallest thing you can see is maybe a rock the size of maybe just a bit longer than your forearm. So this is really high resolution imagery, and it's actually better than most imagery that we get from space of Earth. So this slide shows one of the mosaics that I've made just in 2D. So this is 6 meters per pixel. So you have Gale Crater on the left, and then on the right you have my study area in the highest resolution, which is called high rise. And so this is a river channel that has formed on the side of Mount Sharp, and it's really exciting because if you look closely, you see all of these lines in the side of the channel, and these are exposed layers. And layers are really exciting as a geologist because they are a time machine into the past. So the further down you go into the rock record and look at these layers, the further back you're going in time. So if we understand how these layers relate to each other, and maybe even their composition, we can understand how Mount Sharp formed, and if it was water, if it was wind, and whatnot. So here's a little graphic showing the principles of stratigraphy. So stratigraphy is the study of layers in the geological record. So on the right, there are the 5 laws, or really the 4 laws of stratigraphy, which essentially boil down to rock or sediment will deposit in a horizontal way, and older layers will be on the bottom, younger layers will be on top. So if we see any change to that, if we see any of these layers at angles, for example, to each other, or if a layer is missing, then we know something has happened. There was some sort of process, whether it was a large-scale process like folding, or water level rising or falling, or maybe even dunes migrating, or maybe something more local like erosion, like a river forming and washing away material. So if we can understand these relationships, we can think about how did the rock form, what was the environment for the sediment when it deposited, was it in water, was it in air, and if there was water, how long it persisted. So whether all of the rock seems to have been deposited in water, or if there were sequences of wetness and dryness, this is all information we can use to reconstruct the climate of Mars. This is a video that I've made of the data set. So in the software I have the 3D data, and then the image is actually draped on top of it. So we get this really beautiful 3D visualization of this scene. You can see loads and loads of these layers, especially as we're flying through. They're actually 3D, which is really exciting for me as a geologist because this looks a lot more like what you would see in the field. This channel is actually really, really big. So it's about 2.4 kilometers across and about 800 meters deep. And here we are circling around one area of interest where you're seeing lots of layers that seem to be repeating, which is really exciting. So there's some sort of process that may have been repeating over time. So here's the software that I use. This is called Pro3D, and it is a software that's actually being developed for operations purposes for PanCam. And PanCam is also called the eyes of the ExoMars rover. So it's a pair of stereo cameras that will be on the rover and take 3D images of interesting geology on Mars. But I'm actually using orbital data in the software to do the types of analyses that Mars geologists will do with the images of ExoMars. So you can see, very similar to the video that I showed you, a very lovely 3D view of the channel. If you're wondering if I get motion sick while doing this, yes I do. And here are these exposed layers. It's just incredible to do this work and get to look at these images all day. So something very special about this software is that it has loads of virtual tools to actually function like a geologist. So if we want to take a look at the types of work that I've done, I'm currently tracing out the beds on either side of this channel. And this is really helpful because it helps me familiarize myself with the layers, understand their relationships with each other, and also correlate them across either side of the channel. And then from here, I'll actually take measurements of the thicknesses of these layers, and then also project planes through these sets of layers to figure out their actual orientations. And initial results from using this software have shown most of these layers are very horizontal, and that would suggest deposition either just by wind or maybe in a lake environment rather than any sort of volcanism or anything else forming Mount Sharp. Sometimes, even as a geologist, when we look at these 3D images, it could be really easy to lose perspective. So I made this little movie that I'll show you just now, showing a 6-meter astronaut, I'm pretending I'm much taller than I am, standing at the edge of the channel and zooming out as if there's a camera above them, and showing you the type of view someone might have in this river channel. Here's the astronaut. It's just a little black speck, and it gets smaller and smaller. So you can really see these layers are actually really huge. And if someone were to be in this river channel, it would be a spectacular view. And so I've also shown you here at the end an image that I processed for artistic sake. And so it's the view of the astronaut, and if you squint, you'll see them standing on the edge just where they were in the video. And cast over the channel is the Mars sunset. So sunset on Mars is blue rather than red due to the scattering in the atmosphere. And so I've used images that Curiosity has taken of the sunset to simulate what it might be like to stand on the edge of this channel and watch the sunset. And I just wanted to finish there to, I guess, take us away from the technical geology and really just think about how 3D can help us really experience the surface of another planet. Thank you.